Hello, everyone. My name is Terry Erzman. I'm the Vice President of Marketing for Citus Data. I'd like to welcome you to today's webinar. Before we get started, I'd like to just go over a couple of housekeeping items. First of all, if you can hear me, would you please raise your hand in the GoToWebinar control panel on the right? Great, I see lots of hands raised there. Thanks very much, everyone. If you have questions during today's webinar, please enter them in the questions box in the GoToWebinar control panel, and we'll answer as many of those as we can at the end of the presentation. We will be recording today's webinar, and I'll send out a link to the webinar recording once it's posted on YouTube. So you can look for that if you'd like to review parts of the webinar or send it on to some of your colleagues. We will also, if there are extra questions we can't answer today, we'll answer those in a blog post following the webinar. So we'll give you further information at the end of the webinar if we have more questions and we had time to answer today. With that, I would like to introduce our speaker for today. Utku Asman is with Citus Data, and his topic today is powering real-time analytics and data ingestion on terabytes of data using Postgres. Utku, I turn it over to you.
Thank you, Terry, and hello, everyone. Good morning and good afternoon to those of you joining us from the East Coast and also in Europe. So my name is Utku Asman. I'm an R&D director at Citus Data. So as Terry said, today I would like to tell you how we use Postgres to enable real-time analytics on very large data sets. Now the word real-time is a bit overused and it may mean different things to different people. So I'd just like to take 30 seconds and give a definition of that. Here, when we say real-time, we actually mean two things.
Sorry to break it. Right now, we're just seeing a black screen.
Okay. Well,
there we go. You're all set.
Okay. Sorry, I just realized I had to click on it. Okay. So, by real-time, we actually mean two things. One is ingesting data in real-time and updating it in real time. And second, we're talking about our serving our end users with insights, real-time insights from this data. So today, we're going to go into technical details of how this is possible, but also we need to cover quite a lot of topics. So we may leave intentionally some of the details out. If you have any questions, we'll try to take them at the end of the presentation. And for those questions that we don't have time to go into, we'll try to answer them over email, also in our blog on our website. So with that, let's start talking about the problem before we actually talk about the solution. Now, there are multiple factors that define the real-time analytics problem today. And the first one is just sheer size of the data that we need to be looking at. In a recent survey done by Wikibon, we see that more than half of the projects that are labeled as big data projects, people are dealing with data sizes of greater than 50 terabytes. Actually, for many of these, the size is even more than 100 terabytes. So this is a major challenge. We need to change our mindset to be able to deal with this amount of data, and we've come here quite quickly compared to, say, even 5 years ago, where we were talking about probably an order of magnitude less amount of data. But that's not the only challenge. Now, we also need to give our end users, who in this case are humans, the ability to interact with these very large data sets in real time. Long gone are the days where we could do some batch jobs overnight, create some static reports, and provide it to our end users the next day. Most people now want to have access to tools where they can interact, they can play around with what they want to see, and in a very responsive way see the results they want. Now, another challenge in trying to do this is the rate at which our data changes. Now, even in a matter of minutes, our data becomes outdated. So we really have to keep up with the velocity of the data that we're showing. And while doing this, we need to manage the complexity and cost. While the demands on what we need to be able to show, the tools that we need to give to end users are increasing, at the same time, also the demand on increasing the productivity and efficiency of our systems are increasing. Now, what is the solution? Well, the solution has multiple components. One, well, we need to be able to provide fast analytics, because we said we have very large data sets, they're growing, and we want to be able to give some interactive access to our end users. So for that, we need very fast analytics. And then we need scalability and high availability, because our data is growing, so we need an infrastructure that can grow with it. And we have end users. This could be customers or internal customers, such as data scientists in our companies. So we have to keep these systems up and running. And then there's the real-timeness of data. As we discussed before, data gets outdated very quickly. Not only that, but we also want to be able to integrate all these pillars together. And currently, the way we do it is we need to use multiple technologies. For analytics, we might have our scalable data warehouse solution. But then, to keep data fresh and up to date, we rely on our operational systems. And then sometimes to even scale in the way we want, we even need to integrate these in very complicated ways, or even rely on, say, Hadoop clusters on the back where we archive some of the data. So at the end of the day, what we see often is something like this. To be honest, it's really a big mess. And this is mainly driven by the divide between operations and analytics side of things. Because for analytics, usually the most efficient way of doing it right now is batch loading your data and then running some fast analytics on it. But then you have data that's changing in real time, so you need to rely on your operational system to do that. And then you need to connect these two, integrate these two sides. And this creates a lot of complexity. It becomes very expensive. There's an alternative approach to the solution, which is, what if I could have one database that combined these three pillars? And on top of it, it came with a community-driven and open ecosystem. Now, I understand the three pillars. Where does the community-driven and open ecosystem come from? Well, it comes from the fact that we want our technology to adapt to trends, adapt to needs. And that's exactly what a community-driven technology does. And we also want to have options. We don't want to be locked into a black box that we don't understand what it does. And finally, we want something that is extensible, because today we're using technology to create a competitive edge. And only with a technology that's extendable, we can differentiate ourselves and build something that really puts us in front of the competition. So, okay, this approach seems to make sense. Now, why Postgres, though? There are other solutions that might be community-driven, other open ecosystems. Why Postgres? So Gartner, who have been focusing on the enterprise space, now say that in about 3 years' time, more than 70% of the new in-house applications will be developed using an open source database management system. We started seeing this trend in startups and more technology-savvy companies a few years ago, but now it has moved to the mainstream. Now, this still doesn't explain exactly why Postgres, but maybe the next survey does. This is actually pretty interesting. In Hacker News, when people were asked in 2010, which database do you use for your projects? Number of people who said MySQL were more than Postgres and MongoDB combined. Now, 4 years later, in 2014, same question, and things looked very different. Now, it's almost that number of people who say Postgres are more than MySQL and MongoDB combined. So then, we're definitely seeing a trend towards open source RDBMS, and we're definitely seeing a trend towards Postgres. Now, a Hacker News survey doesn't really show the worldwide usage stats, but what it shows, the trend among developers and technology-savvy companies. That's why it's so important. Of course, this is one side of the story why in this picture Postgres makes sense. Another reason is that from a technology point of view, Postgres is very extensible and it has a very powerful API framework which lets us use it to build the technology we want. So we'll get into the specifics of that. But before we do that, so who are we to talk to you about this problem and a potential solution to it? Well, we're Citus Data. We came out of the 2011 fall Y Combinator batch, and we're based out of San Francisco since then. We built Citus DB, which is a scalable Postgres solution. And part of the technology that goes into Citus DB, we open sourced, specifically a Columnar Storage extension and a sharding extension for Postgres. Now, the concepts we're going to discuss today are concepts we've used in building Citus DB. So we will also be able to show you some real-life applications of these concepts towards the end of our talk. So with that, just a quick teaser on what the end result looks like. Once we build our system, what can we enable with it? Well, you can, whether it's your interactive analytics dashboard or it's, again, a mapping application that serves end users, what we'll be able to do is, in the backend, analyze billions of events and apply hundreds of filters on the fly and still get responses in seconds or even less than seconds. And do this while serving millions of end users with our dashboards or applications. And at the same time, update the underlying data in an extremely fast manner. And we'll be able to do all of this with the simplicity of maintaining just one single unified database. Now, we'll give a specific example of how Cloudflare does all of these at the end of our talk. But first, let's talk about how we make it possible. Now, going back to our approach, we said there are the 3 pillars, and then there is the integration with Postgres. So let's start with the Postgres side of things. So what we did with Citus DB, and what really worked well, was extending Postgres as opposed to forking Postgres. And the distinction is that once we extend Postgres, we can continue to benefit from the latest advancements. For instance, going back like a decade or more, with every major release, Postgres has been increasing its performance by 40%. And innovation keeps on going. With the latest version, now we have JSON-B, a very efficient and fast way of processing JSON documents. Now, then when we extend Postgres, we also remain in sync with all the new data types, extensions, and tools that come with it. And we're able to leverage a very vibrant community and open ecosystem. Now, how do we do this? How do we extend Postgres as opposed to taking a particular version and forking all from it? Well, we utilize the hooks mechanisms in Postgres. Some of you may already be familiar with them. Essentially, Postgres allows you to intercept certain processes and basically use Postgres internals while still giving you the ability to extend and build functionality on top of it. Another thing we use is the foreign data wrapper framework. This lets us use a very powerful API framework to write our own storage engine in a way that we remain compatible with all the data types, and we used some of the Postgres internals, such as the optimizer that makes really good use of the statistics you collect on your data. And by utilizing the hooks and using foreign data wrappers, we're able to remain in sync with every major release, because the actual code, Postgres code we change is minimal. Most of the stuff is things that we use write using APIs and can be rebased pretty quickly once a major release is out. So at the end of the day, once we build our system by extending Postgres, what it looks like is it becomes essentially a drop-in replacement for Postgres. So on top, I still have my analytics dashboards or front-end applications. At the bottom, I have my multiple data sources. And in this picture, normally on a single machine, I would have Postgres in the middle. Now I replace that with a scalable version of Postgres by keeping still the flexibility and familiarity of it, by supporting the data types, extensions, connectors, tools, etc. But instead of just having the power of one machine, I can utilize the power of hundreds of machines by scaling Postgres in this way. Okay, so we'll do that, but then what about the remaining three pillars? How do we achieve basically a fast analytics, scalability, and real-time data? Let's start with fast analytics. To be able to deliver analytics fast enough to run on terabytes or even hundreds of terabytes of data, we need to achieve massive parallelization. So for that, the first thing we employ is this cluster architecture, where we have a master node. This is essentially a coordinator node, and many worker nodes underneath connected to it. And the second thing we do is we take your data and we divide it up into really small blocks that we call shards, and we distribute them across the cluster of worker nodes. And then what we do is we distribute your queries. So the end user interacts with the master node as if she's interacting with a single Postgres machine. But then the master node takes this query. Well, the master node actually doesn't hold any of the data. It just holds metadata, which tells it where each of the shard is and what kind of data is in each of the shards. So then it takes this query and then generates many, many queries from it and sends those queries to individual shards, relevant shards. Now what this achieves is actually parallelization within the node and across the cluster. Because Postgres is not multi-threaded, so when you run a query on Postgres, you're just utilizing one core, even if you have a multi-core machine. But doing it this way, say in this example, Citus DB master node would take the query, and let's say that query, the data that's relevant to that query is in shards 1, 2, and 3. Then it would send 2 queries to node 1, and each core is in parallel will start processing those queries. And same thing goes at every node with relevant shards. Now, when you scale this out to millions of shards, essentially you get a massive level of parallelization, and you're able to use hundreds of cores in parallel. But to be able to do this effectively and efficiently, we need to push as much of the compute as possible to where the data is. And let's discuss that a little bit. So earlier distributed systems followed a pool data to master approach. So what that meant was I had my data nodes, but then when I wanted to do a calculation on it, I had to pull large amounts of data into my master node and do the computation there. Now obviously this had major problems because suddenly my network I/O could become the bottleneck, or I would rely heavily on one master machine to do the computation. So this really didn't scale well. So instead, what we need to do, and what we did in Citus DB, is push the compute to data. And here's a simple example of how we went about doing it. assume that we want to take an average and a maximum across a range of values. Now, we send that query to the master node. Then the master node parses this query and converts it to a parallelizable form. Now, in this case, I cannot actually take an average at each node and then combine them in the master node. That wouldn't give me the right result mathematically. But what I can do is I can do a sum and a count at each node. And then I would only transfer those results back to the master node. So we're talking about very small data. Now for the maximum, actually it's easier. I can just take the maximum at each node, and then I can collect the maxima and then take their maximum to compute the global maximum. Now, of course, this is a very simple illustrative example. But when you think about you need to do this for the complete SQL, and also you need to be able to support joins between distributed tables, then it becomes an interesting problem to solve and a difficult one. But that is what we did, and that is what we solved. And in most of the cases, as a result, what we're able to see is that we can linearly increase the performance with the number of nodes, actually the number of cores we have in the system. Now, there was only one part of achieving fast analytics, perhaps the most important part, but then there's also the issue of columnar analytics. Now, it's widely known the benefits of having columnar storage for running analytics queries. So we built a columnar extension for Postgres, which also uses with the scalable form of Postgres, which is what's employed in Citus DB. Now, again, let's go over this example here. When I have a very wide table, in this example 700 columns, and then I have millions of rows, say my query only is, for my query only 4 or 5 of the columns are relevant. In a role-based database such as Postgres, even though I only need to read those 5 columns, because data is kept in a role-based format, I would have to sequentially read the whole table, essentially all 700 columns. This results in very large amounts of unnecessary I/O, and it's very costly in terms of query performance. Now, when you have a columnar store, what you can do is you can only read the relevant columns and save significantly from your query performance. So that's one of the advantages of using a columnar storage engine on Postgres. Columnar projections, you read only relevant columns. And you still get the benefits of, depending on, of course, how you implement columnar engine, but for the one that we open source for Postgres, you can use skip indexes, so skip over irrelevant rows. And thanks to the foreign data wrapper framework within Postgres, we were able to integrate it very tightly with Postgres internals and avoid a lot of the overhead of having foreign tables. Now, another benefit of columnar storage is the superior levels of compression. Since the data I keep in a column is usually very similar, I can get very high levels of compression on it. And in terms of just analytics performance, this helps me because I reduce I/O, but also because I can fit more data in memory. But actually the benefit goes beyond than the speed of analytics, because suddenly I can actually store a lot more data on my hardware, and my storage costs come down per, say, unit of data. And here is an example of what's possible today with the columnar store on Postgres. We've used TPCH data, and of course, depending on your type of data, the compression rates change a lot. We've seen as much as 10x compression rates using our columnar store, but perhaps 4x on average is a more realistic figure. And even within TPCH, with different tables, you see different levels of compression. But it's safe to say that you get 3 to 4x for most data types. And as we said, this is a huge benefit in terms of fitting more data in memory and also reducing your storage costs. So now, what does it all mean? Bottom line means fast analytics. So actually, we put Citus DB side by side with 2 of the very popular analytics SQL-based analytics solutions that also run on open ecosystem, in this case Hadoop. so Impala and Spark SQL. And in 8 of the 11 queries that we were able to run on at least 2 of the systems, Citus DB came out on top, and often with a big margin. So this is basically, this shows that Postgres can be made faster than Impala and Spark SQL. And of course, when we put Citus DB and compare it with vanilla Postgres, then you get essentially more than 100x. This is a function of obviously the hardware you use and the cluster size you use, but it's possible to go 2 orders of magnitude or more. Now, for more details of this benchmark, please visit our blog. We try to make it as transparent as possible, and we would welcome any feedback on the methodology or the results. Okay, let's move on to scalability and high availability. Now, if I want to talk about scalability, actually, I probably need to start talking about high availability first. Because when I horizontally scale, then just law of large numbers, the probability of something going wrong increases. I have so many machines, I have so many more hard disks. So then I really need to solve the issue of high availability before I can even start talking about scalability. And when we go back and look at our block-based architecture, remember we said we're going to divide your data into small shards. Now you can specify how big these shards can be, but to give you an example, 512 megabytes or 1 gigabyte would be a typical shard size. I need to be able to replicate my data. Now we do replication on a shard by shard basis. So, and you can specify what kind of a replication factor you want to use. Well, the minimum should be 2 for you to get any benefit out of it. But in this case, we're looking at a replication factor of 2. So we create 2 copies of each shard and distribute them across the network in such a way that no worker node is an identical copy of another one. Now, this becomes quite important when we talk about failure handling. Again, let's look at an example, actually the same example we used before. Now, I receive a query. My master node knows which shards needs to hit. And in this example, for simplicity, we said that I have a 4-node cluster, and then there are 3 shards at each cluster that are relevant, that will be queried. Now, let's say one of these nodes go down. Now, as we said, the replicas for the 3 shards that were on node 3 relevant shards, are distributed across my network. So they're on multiple machines. And in this case, nodes 1, 2, and 4. Now, what would happen is the master node, it tries to access node 3, and then it cannot. So then, but it also knows where each of the replicas are. So it would redirect the queries and access the replicas. And it would do this in real time and basically would complete the query. Perhaps with a little bit of a delay, but the query would still complete. And this is what we mean by mid-query failure handling. Now, of course, the advantage of this is that, as you can see, the extra burden of losing that node, the extra workload, is distributed across my cluster. So in this case, 3 of the nodes are picking up the workload of node 3. Now, if you have a bigger cluster, say 10 machines, basically, roughly speaking, the cost of losing 1 node would be about a 10% reduction in overall performance. For a larger cluster, the user hardly notices any performance difference when a node goes down. So this is all possible thanks to the logical sharding, the small block size, and the way replication is done and handled. Now, okay, we've sorted out high availability, then let's talk about scalability a bit. So I set up my initial cluster, I have 3 nodes, but then I have more data. And then I want to be able to keep the same level of performance I had before. So what do I need to do? I need to add more hardware. And it's very easy because all you need to do is you add the hardware and then you tell the system that you want to rebalance your workload. And then the system would start taking these small shards and moving them into the new node until there is like a uniform distribution of your data. Now, since each of these blocks are pretty small, the impact you have on your network and on your hardware performance is minimal. You can actually even control how much of hardware resources you want to dedicate to the rebalancing action. So at the end of the day, basically you can dynamically scale out without taking your system offline. While you're still using your system, you can add a new node and gradually move data. And once you start building data on this new node, queries will start hitting that node and essentially bring its storage and processing power into your pool of hardware resources. Now, bottom line, what this all means that scalability, that just works. I can take my Postgres database and I can scale it across hundreds of nodes, thousands of CPU cores, and potentially petabytes of space. I can do this on SSDs, I can do this on rotational disks. I can also increase the total amount of memory that's available to me. And I don't have to know exactly how much resources I'm going to need, like from day one for the future. As my data grows, I can adjust by adding or removing nodes, and I can do this in a way that's pretty seamless. And this whole cluster will provide me high availability. There won't be any single point of failure, and I'll be able to recover from failures in real time, even during its queries. So moving on to our third pillar, the real-time data. So in most of the scalable analytics systems, what I'm used to doing is taking a snapshot of my data, batch loading that data, and then running analytics on it. There are two potential issues with that. One is that my data becomes outdated very quickly. And second, this requires me to have some complex integration. So I need to have a system which can handle the real-time changing data. But then I have to move my data from there to the analytics system, and I have to keep doing this. That's why when we first solved the issue of fast analytics and scalability, the #1 feature request that came from our customers was the ability to do real-time inserts and updates. Now, this is actually conceptually very easy to explain. So what I want to be able to do is I want to be able to insert or update my data, and I send that query to my master node, and the master node would figure out which shards it needs to hit, and then also which replicas it needs to hit, and it would just direct that query and update the data or insert data in that particular shard. Now, obviously, this is quite easy to explain, but when it comes to implementation, you really have to think about how you partition your data and how you handle failures when you're doing the inserts and updates, and it becomes quite complicated. But as of now, we have actually an extension for Postgres, which does this for Postgres, and we use the technology there on Citus DB to enable real-time inserts and updates as well. So what this means is that simultaneously my system then can handle operations and analytics. And to show you how the system behaves, so as I keep adding nodes on the left side of the screen, you see that I can increase my operations capacity. I can do more and more transactions per second, and I achieve near linear performance increase here. But at the same time, simultaneously, I can also reduce the amount of time my analytics queries have. Again, we see near linear increase. And the ability to do this simultaneously in one single database in a very simple and unified way is really key in solving the problems we mentioned in the beginning of our talk. Well, we're almost there. Just a quick recap of what we discussed so far. We started with Postgres. We said Postgres performance has been going up by 40% with each new release. The innovation continues. JSON-B was introduced in the latest version, 9.4. The features provided by Postgres have actually almost caught up with those of Oracle. And thanks to hundreds of developers contributing and a great ecosystem, there is no end in sight. Postgres provides great tools, extensions, and also people. Now we've taken that and we've taught Postgres new tricks. We've enabled it to do analytics at 100x the performance with massive parallelization and Columnar Analytics. We gave it the ability to horizontally scale and in a highly available way to hundreds of nodes. And with these, we enabled real-time insights on very large amounts of data that wouldn't be possible on a single machine in a unified way. So all these concepts that we briefly touched on now are employed in Citus DB. So we'll be able to give you an example of this in production. For example, we've picked Cloudflare. I presume many of you on the call today will be familiar with Cloudflare. For those who are not, Cloudflare is a content delivery network accounting for more than 5% of global internet traffic. So they have huge amounts of data. They process more than 100 billion network events per day. And they have an analytics dashboard which serves more than 2 million end users, website owners. And to enable this analytics dashboard, they have to, in real time, ingest this very large amounts of data and then serve their customers by enabling sub-second queries across billions of rows. Now let's look at what they've done. So this flow actually is taken from the Cloudflare blog. We've also blogged about it on our website and added our comments to it. So essentially what they've done is, and starting from the left side of the screen, they are logging trillions of events, just vast amount of data. But it's so vast that to be able to put it in a database in an economic way, they need to do some pre-aggregation. So for that, they've written their own system using Go, and they've created these tools, essentially a Kafka data queue, which then feeds into some aggregators, which aggregate the event logs data into billions of 1-minute aggregations. Even aggregator, we're talking about very large amounts of data. And then this data is ingested into Citus DB in real time. And Citus DB directly feeds their front end, which is an analytics dashboard, and also the tools their data science teams use internally. And these analytics dashboards and the data science teams, they query Citus DB and they get their responses within a second or two. Now the data in Citus DB is constantly updated and is constantly kept fresh. At this point, I'd like to actually switch to my browser and show you what this dashboard looks like. Okay. Can you see my screen? Presume yes. Okay.
Yes, we can see your screen.
So, this is for a test website what the analytics dashboard looks like. I've just logged in, and by default, it's showing me my stats in the last 24 hours. There's quite a bit of information here. I see requests, I see data on bandwidth, unique visitors, threats. I see performance broken down by different categories, security measures, geographical information, and other statistics. Now, bear in mind, these have been just calculated once I logged into the analytics database. Now, let's say I want to see what happened in the last month. I click that. Okay, so to see the difference, let's just go and do this again, looking at requests. All right. Okay. So this was my original screen after I logged in. Now I want to see what happens in the last month. And in a few seconds, it updates, and it actually has recalculated all of the metrics that we looked at before. Now imagine doing this, being able to do this for 2 million plus websites and showing results in such a responsive way. That's essentially what Cloudflare has done. Now I will switch back to the presentation. Now let's look at what worked for Cloudflare. Well, the first thing was doing this in a way that's very compatible with Postgres. From day one, Postgres has been their trusted database. They love its reliability, they like its extension mechanisms, the fact that it supports multi-structured data, they love the community, the documentation. And now being able to just use all that familiarity, but in a way that serves their other needs was great for them. And their other needs were, one, the performance. Now, to be able to get the level of performance that you just saw, actually, we had to shard their data into millions of shards. And the benefits were twofold. One, we were able to prune away the shards that were not relevant. So in the example, when I was looking at 24 hours of data, because of my sharding, I could quickly focus on just the time duration that's relevant to me. But then even for that time duration, I have many shards across the cluster. So I'm able to utilize hundreds of cores to process that data. And I can do this for concurrent users. Now, the flexibility that Postgres provides with its different data types, its different functions, the scalability and accessibility of this block-based architecture and the fast analytics built on it enable this kind of performance. And this performance is not only for the customer-facing dashboards, but also for the data scientists within Cloudflare that need to run business intelligence queries that go across customers. Essentially, some of their queries have to read through billions of rows, and the results are still very responsive, matter of seconds. Another thing that worked really well for Cloudflare was that they were using some Postgres extensions, especially HStore, which is essentially a key value data type. They were using HStore to keep their sparse data efficiently compared to a purely relational table format. And also hyperlog extension, which lets them do very fast unique count approximations. And the cool thing about HLL is that you can specify how accurate you want it to be and control kind of the trade-off between speed and accuracy. And now with CitusDB, they could not only continue using these extensions, but they could speed them up and by parallelization. Now, they tell us that they also like the dynamic scaling option because their data has been growing and they can just seamlessly keep adding nodes and keep the performance expectations and answer the key performance expectations. Now, of course, high availability is a must for them. When you have 2 million plus users that could access your system at any given time, your system simply needs to work. To summarize where you can apply these concepts and actually where we have applied them using CitusDB, Cloudflare is a good example of real-time analytics, being able to ingest data in real time, update it in real time, and then serve it to end users in a very responsive, fast way. It's also a good example of a use case where you can scale. You can start from your single machine Postgres and scale it out and make it highly available. But there are other use cases where these concepts we described apply as well. One of them is you could power more interactive dashboards. So going back to Cloudflare's dashboard, it does show a lot of data, a lot of different types of information to me, but really the only point where I interact with it is when I change the time dimension, the time period. Now, I can actually create a lot more interactive dashboards. An example is doing funnel analytics. So imagine I'm providing an analytics service where I track users' behavior on a website or on a mobile app. My end user can log into the system, and for their website or for their mobile app, they can create a custom funnel to look into how users had behaved on their website. For example, they would predefine, say, hundreds of events. And then on my analytics dashboard, they would say, okay, first step, show me users that have come to my website between such and such date. Second step, the ones that clicked the video. Third step, the ones that signed up on my newsletter. And then click run query, and in a matter of a second, they would see the funnel, basically how many people that meet this criteria. So this is a real-life example, and all of this is possible thanks to different data types and flexibility of Postgres and the scalability of the approach we just discussed. Another use case that's actually becoming more popular now is NoSQL use cases. Now with JSON-B in Postgres 9.4, actually some benchmarks show that Postgres can handle JSON documents faster than MongoDB. And with the real-time inserts and updates functionality we've shown, essentially we can use that functionality to do low latency writes and short requests. So suddenly your scalable Postgres actually becomes a NoSQL system without giving up the power of SQL. Another potential use case would be that you don't have to grow out of a single Postgres box. Let's say you already have a system, but it's a multi-tiered system. You have your operations, you have your data warehouse, you have your analytics, and you just want to simplify it and replace it with one single unified database. So you could do that as well. This wraps up my presentation. And for your questions, you can email engage@citusdata.com, or you can email me directly at utku@citusdata.com. You can visit our website and also our blog, where we discuss Postgres issues, scalability issues, and real-time big data issues. I believe we also have some time now to take questions, if there are any. Terry?
Yes, again, if you have any questions, please enter them in the questions panel in the GoToWebinar control panel. So first question, maybe you can just expand on this, you touched on a little. How do you work with unstructured data, and how are you related to the growing Hadoop Spark-like ecosystem?
Okay, so essentially Citus DB is an extension of Postgres. So the way we handle multi-structured data is through what Postgres supports. And Postgres for a while has had the HStore data type, which is a key value pair, so which lets you keep semi-structured data in your database. Excuse me. And now it also has support for JSON-B. So that is how we would, so whatever you can do with Postgres in handling semi-structured data through JSON-B, through HStore, you can do it with Citus, but now with the power of a much bigger cluster. So you would be able to actually do things a lot faster than what you can do with a single box Postgres. Now, in terms of how we're related to some of the Hadoop-based solutions, earlier versions of Citus DB, we actually did write a connector that would read data on HDFS, and that will let you run Postgres on HDFS. You can reach that connector on our GitHub page, and we've open sourced it, but we're no longer supporting that project, because what we found is that almost all of our customers who wanted to use Postgres wanted to get the full advantage of Postgres. So they prefer the existing system where we keep data in as Postgres tables as opposed to HDFS. So we're not directly related to then Spark SQL and other Hadoop-based solutions. But if you want to experiment playing with Citus DB on Hadoop, please visit our GitHub page, and there will be some resources there.
Okay, next question. Since there's only a single master node, is there a limit to the amount of inserts you can achieve per second?
Okay, that's a very good question. Currently, the system officially out of the box supports a single master node. And then there are some limitations to the insert rate. But we are working on a multi-master solution, and we plan on actually deploying that later this year or maybe next year. We've already done some tests, some prototyping, and we see that we reach hundreds of thousands of insertions per second with a multi-master approach. But that's not in the official product yet. It will be.
Okay. Next question is, how does your engine handle aggregates that are not min, max, sum, etc.? For example, HLL ag or array ag.
Okay. So I'll give a very high-level answer, and for a detailed answer, please email us, and we'll be happy to share more details with you. Now, obviously, there is a limit to how much parallelization you can do with certain parts of SQL, and one way of dealing with them is actually pulling data to the master, at which point you lose basically the benefits from parallelization. So we either do it that way. If it's impossible to parallelize the function, we can do it by pulling the data to master. The system allows you to do that. Or oftentimes what we see is that we can, depending on your use case, we can remodel your data or rewrite your queries in a way that you get the full benefit of parallelization.
Okay, next question. How does Citus DB compare to distributed column stores such as Amazon Redshift or Vertica?
Okay. So just looking at the analytics side of it, it basically provides a similar level of functionality. But then with Citus DB, you also get the ability to do real-time inserts and updates, and also being able to use all the tools and extensions and functions written for Postgres. So that would be the main difference.
Okay, next question. How do backups and streaming replication work with Citus DB?
Yeah, we have customers that are using streaming replication and backups, basically all tools. Now, in the system, essentially every node is a Postgres database by itself, so you can use streaming replication and backups in the same way you would do on Postgres.
Okay. That's all the questions we have right now. If you have any other questions, please feel free to email them to us at the addresses on the screen. We thank you for attending today's webinar, and please check back on our webinars page for upcoming webinars as we're constantly adding new ones. Thanks, everyone.
Thank you very much for listening.
Have a good day.
Have a nice day.